Okay, so we're talking about electrochemistry still, and cell potentials. And I don't know if Hagar the Horrible's still around, but I like him. And he's talking about how he can, right? There's only one thing that'll defeat his plan to conquer the world, and superior enemy forces, rust. Right? It's pretty hard to stop rust until they figured out the answer. Sacrificial anodes. These things. Right? So the sacrificial anode will rust, it'll disappear, it'll react. Right? And once all the sacrificial anodes are gone, then rust will start. So it's kind of interesting. So it's kind of like thinking of it this way. The boat's cast iron, right? It's the cheapest metal, so that's why it's cast iron. They don't make the whole, it would make more sense if they made the whole boat out of this material, right? But they can't. So anyway, so the whole boat's cast iron because that's the cheapest metal, toughest and most durable. So they attach all these hunks of zinc to it. Why? Because zinc will react before the iron will. So once all that zinc's gone, though, then you're gonna every place where there's a little scratch or whatever, that's going to start rusting because the rest is painted over. So that's safe. Okay. So these sacrificial anodes are pretty much everywhere because iron's everywhere. So 4 years ago, I thought, man, how long is it going to take? So I put up a fence in our backyard and threw one of the galvanized nails in here, and the other nail is, a typical nail. And you can see there's a huge difference there. Now the zinc one, the zinc-coated nail, the galvanized nail, that's that sacrificial anode, it's finally starting to rust. It's taken 4 years, and it's still a solid nail, though. Okay, so some terminology. We need to get used to this terminology. So I think the homework can be confusing because they're very wordy questions. And the very wordiness of it, cell potential, cell voltage, electromotive force, EMF, E-cell, they're going to use all those words and they all mean the exact same thing. Right? They all refer to the reading on the voltmeter. So, Bowdy, what's a voltmeter? Thing that measures volts. Great. Okay. So, Andromeda, how many volts are on this battery? Those big A batteries. How many volts are there? Anybody know? You guys don't know your batteries? 1.5 volts, right? 1.5 volts are these big batteries. So, but on the package, right? If there's all these batteries and these packages, and you're going to buy one, don't you buy the one that has, the expiration date of 2020 instead of 2017 or something, right? So how can they do that? I mean, what are they going to do so that this thing is going to last a heck of a lot longer? Put 2020 on this. The trick, I'm going to show you the trick. This is supposed to be how many volts? 1.5. Okay, so when I connect a voltmeter, which one goes where? Well, you guys are battery dummies, you wouldn't even know, right? This guy's the plus, that guy's the minus. All right, so hook the red up to the plus. Now you got to tell me what it says there. Black to the minus. And it reads 1.57. So that's what they do. They put in more than 1.5 volts in there so that it'll slowly decay in the package for years, but they put in over 1.5 volts in the first place. But so there's a redox, electrochemical reaction going on inside that battery, and once all the reactants are done, the battery's dead, right? And that voltage will slowly fall off as those reactants get consumed. Okay. But the point I'm trying to make is that all these words up there, they all refer to the same thing, refer to what's read on the voltmeter. Okay, and just kind of remember that. That'll help you out. Maximum electrical work. So, Wmax, you can answer questions like, find the maximum electrical work when 45 grams of silver is produced in a voltaic cell with EMF of 1.15 volts, and they give you a reaction. So they're just trying to say that, for example, inside this battery, right, they're not going to have silver. Silver's way too expensive. But they'll have reactants in there. And once those reactants get consumed, right, it's dead. But how much work can you get out of this? So instead of talking about your little remote control car going across a table for so far and so long, there's so many different problems that this battery could be used for. So they just use it as work. Calculate the work. Calculate the energy. What is the unit for work? It's what? Work is force times distance, yeah, but the unit is joules. Work is energy, right? So you better get units of joules for it. So when we get W max, yeah, we better get joules, okay? So this is what we're going to use to calculate the work, right? So this will be in units of joules, right? Our E cell, that's in units of volts, right? See, it's already confusing. Look at that. They picked the word E cell. It's whatever's on the voltmeter. Remember, all these mean the same thing. So these are all volts. So that one's volts. Okay. So if we're going to calculate this work in joules, we need to know what the voltmeter reads. So they're going to tell you that, right? You can't figure that one out. They're going to tell you what the volts are, the E cell. But N and F, you're going to have to figure out. Now, F is the easy one. F is called whose constant? Starts with an F. Faraday's constant. And it is 96,485. But units are important, even though they're all going to cancel out on us. 96,485 big C's per mole of E minus. What's a big C? Steph, what's a big C? Give you a hint. We have all these electrons, right, moving around. It's the charge. So this is the charge on 1 mole of E minuses are probably electrons. So if you take 1 mole of electrons, 6.022 times 10 to the 23rd electrons, that's the charge, 96,485 coulombs. Okay? Because remember, this whole electrochemistry thing is electrons being transferred from one reactant to something else, right? So let's make those electrons travel through wires and do some work. Turn little motors, turn little gears, okay? So if you have 1 mole of electrons produced, you get 96,485 coulombs. So that number, that's what you plug in for F every single time. It's just a constant. Like you guys already said, Faraday's constant. So, oh, E cell. Where do you get that again? Jose, where do you get the E cell? It's the volts, right? It's from the voltmeter. But I think once you see the volts, that's the number you're going to plug in there, right? That one's kind of easy. So N is going to be the tough one. N's the one we got to do some work on to get. How do you get N? Hint. There's a hint, though, how you get the N, Andrea. N is the number of moles of involved during the reaction. It can be found using an appropriate half reaction. Electrons. The big hint, I think, is F is per moles of electrons. So those moles of electrons have to cancel, because that's what N would be, the moles of electrons. So we got to figure out what N is. That's where this whole problem comes in. So let's try this. Let's solve the above problem. Find the maximum electrical work. So we want W max equals question mark. What is it? Okay, we have 45 grams of silvers produced. Voltaic EMF. Okay, well, let's write down our equation, just start plugging stuff in here. Minus N F E cell. All right, we'll figure out what N is later. Let's just plug in the rest. F is what again? 96,485. I guess we can just write it up here. Might be quicker. Right? 96,485. What are you going to use for E cell? 1.15. So the problem is just getting that N. Okay. Now the hint says we can find N by using an appropriate half reaction. That's the hint. What half reaction? The silver half reaction. I agree with Megan. Connor, how can you write the half reaction involving the silver? Now, why did you say the silver, though? Ah,
45 grams of silver.
That's weird. Yeah, because of the 45 grams of silver, exactly. Man, this happens once in a while. It's weird. I don't know why this happens. Gosh, it's all locked up. What the heck? Yeah, okay, we're on day 35. Ah, it's back. Okay. Okay, so Connor, you're right. You picked the silver half reaction. So because it involves 45 grams of silver. So what would be the half reaction? What would you write?
Ag plus.
To Ag solid. E minus on the left. Does everybody agree? Perfect. Okay, because pretty much all we got to do, we should go back to what we had here. We had W max is minus N F E cell. And you guys already told me this one is 1.15 volts. This one's 96,485. We got to get N. And what we're going to do is convert 45 grams of silver into moles of electrons. That's what we got to do. And whatever we get, that's what we'll plug in for N. And we have our mole bridge, right? So if I want to convert 45 grams of silver to moles of electrons, Jose, where should I start? Now you can do that whole box thing. Start with what? Start with 45 grams of silver. And then even if life looks confusing, no worries, because this unit analysis, dimensional analysis, units always cancel. So Andrea, what should I do next? The molar mass of silver, because those grams of silver has to cancel, right? You don't even really need to know how to do this much. And in molar mass, it's always a 1 up there. Periodic table, I've got about 107.8, 107.9, just round it. 107.9 grams. Okay? Now what, Bowdy? Mole bridge, what's the ratio? 1 to 1. 1 mole of silver, 1 mole of electrons. 45 divided by 107.9, about 0.417. So that's the number I'll plug in up here, and I'll get my W max. So we've got negative, what is that? I'm just going to times 10 to the, what, 10 to the 4th. Right? Why is it negative? Right, because W max is minus NFE cell. Why is it negative? Kendall, why is it negative? Is that a mistake? It's not a mistake. It's supposed to be there. When we said exothermic reactions, those were all negative energy because the energy was lost, going away. It's gone. Here, this work essentially is gone. It's supposed to be used up. All the energy in this battery is supposed to get used up, converted to moving a little car around the table. All that energy is getting consumed. So the battery is losing the energy, negative energy. Oh, and units, don't lose the point. Joules, big J. Okay? So calculating maximum work isn't bad. Just identify the right half reaction so you can use a mole bridge. It's not always going to be 1-to-1, right? Some half reactions involve 2 electrons, 3 electrons. Okay. Yes? This is all multiplying. N times F times E cell. So 0.417 times 96,485 times 1.15. But I wrote it in scientific notation. Standard cell voltages. Okay, so what's kind of nice is you don't have to build all these cells to do the chemistry. Because if you make all concentrations 1 molar, gas is all 1 atmosphere, temperature 25, right? We can predict what the voltmeter is going to read, as long as everything's at those standard conditions. We can predict what this little voltmeter is going to read, right? We have to build the cells, have all the solutions, have all the little electrodes, have the salt bridge, and we can predict what the darn voltmeter is going to read, and that's really powerful. Okay, and here's the equation you're going to do to get it. E0 cell, and remember the superscript zeros? What does that mean again? Standard conditions. Use tables. Nice. So this is all from tables. So we'll predict what the voltmeter reads, E0 cell, and just add E0 cathode to E0 anode. Okay, and everything is, if it's not in this table, we can't do it, obviously. But be sure to switch the sign of numerical E0 values. Here they are. They're all E0 values right there. Standard cell potentials, half reactions. It says if the reaction is reversed, switch the sign. Let's practice a few of these. Let's say this is our, A is our half reaction. Nickel going to nickel solid. What would you write down for E0? See if you can find it in there and tell me the volts you would use. I hear negative 0.25. You agree? Yeah, it matches perfect. Negative 0.25 volts. Okay? How about B? Kendall, what would you write for B? Now, one thing I think, because you guys haven't looked at these tables before, so one thing that goes in my brain right away is to recognize the table. The table is a reduction table, so it really helps me find things if I realize reduction table. So electrons are always on the reactant side. They're always on the reactant side. So I should be able to find this guy A, I should be able to find him in the table because the electron's on the reactant side. And that's a reduction. Nickel plus 2 going to 0, right? So that's reduction. So I'll find him in the table. This one I will find in the table, but it's going to be flipped. So if I'm going to find B in the table, I have to flip it. And then, well, that's kind of what A was. But what happens to the E0 number then? Becomes positive. Okay. So if you flip, find the half reaction, but it's flipped, so electrons are on the product side, you better flip the sign, whatever it says in the table. Last one. I hear times 3. Everybody agree? So the answer that you would guess is negative point. Oh, we flipped it, didn't we? Positive 0.75. Problem, though. Problem. All we do is we do flipping. We don't multiply through because these are potentials. It's kind of like saying, what's the height of the hill? Oh, it's like 10 meters. Well, if I'm going to go up and down the hill 10 times, well, the height of the hill is still 10 meters. So we don't, it's kind of like, remember the words intensive and extensive? Density is an intensive property. Doesn't matter how much you have of water, the density is always 1 gram per mil. You can have a bucket, you can have a drop. It's always 1 gram per mil. Same with these potentials. It doesn't matter what you do to the reaction. Multiply by 3, 7, 8. All that matters is whether you flip it or not. So since this guy is flipped, the answer is still positive 0.25. So kind of a trick question. Okay. Find the overall cell reaction and the standard EMF for the voltaic cell. Now, when I read a question like this, overall cell reaction, that's my answer. What am I adding up to get that overall cell reaction, Audrey? What am I adding up to get it? The two what? What do we call them? The two half reactions. We have to add up the two half reactions. And then it wants the standard EMF. What was the symbol for that? That E0 cell. And you just add up the E0s in the table. So what we should do, I think, is write the E0s over here, add them up, and we'll get that answer. Right? So try it. Pick out what the half reactions are, find them in the table. Right? Write the half reactions. Add up the half reactions. When you add up half reactions to get an overall reaction, you have to make sure what cancels, though. Do you remember doing this? The E's. You can't have E's floating around. Okay. Are you getting this? Did you get this far?
Yeah.
All right. You looked up the volts, and I had to flip the sign on the nickel one.
Oh, yeah.
Right. The silver one just wrote it down as is. But to add them up, I have to do what to one of these half reactions? Multiply by 2. Do I change the E0? No. So multiply that bottom one through by 2, add them up, see what you get. So there should be our two answers. There's our overall reaction and our overall cell voltage, what the voltmeter will read. Okay. Yep.
No, so I was going to ask something about exactly 4.
Okay. See if you can figure out EX4 now.
With in the first time we did it, when it was the ratio of 1 to 1, that's when we multiplied. What is the ratio for this one?
Yeah, so don't skip any steps, dude. Write out your equation. Write out the mole bridge that you need. And the mole bridge that you need is one of those half reactions.
Wait, which one's the right one? That's fine.
So are you going to use this half reaction or this half reaction?
Using acid.
Yeah, so write out its half reaction, and that'll tell you the mole bridge you have to use. Oh, that's a 5. That should be 1.05. In my table, I thought that was weird. In my table says 0.23 volts. Right? It's weird. The table that you have in your book is 0.25. This one says 0.23. Well, let's just use 0.25 because that's what's in your table, right? That's weird. That should not be. So I would start out by writing the equation, because then logic kind of tells you what you got to do then. Deduce what you have to figure out. W max is minus NF B cell. Yep.
So for this, since the electron is on the right side, does it have an effect on it because on bottom?
Oh, no. All you care about is getting things to convert. Sorry, getting things to cancel. So what's your units right here? 1 mole of what?
SN.
Mole of SN. So mole SN has to be on the bottom.
But it's only going to be 1?
Yeah, there's just a 1 out front. So it'll just be 1 mole of SN for every
Okay, so
2 moles of
so
electrons.
there's 2.
If it'd be a 2, yeah, it'd be 2
Okay.
moles of tin. Yep.
Okay.
Anybody lost on EX4? You may get an answer for EX4. Negative what? Joules? Kind of got that. Did you get it? Who else got it? Mia got the same thing. I bet you that's right. So if you got it, go on to the next one. If you didn't get this, let me help you or ask somebody around you.
Yeah, no, you're right.
This, like, the Molar Bridge and
Yeah, but this part, you didn't write the, you have to write the half reaction. It's not always 1 to 1. It's 10 goes to 10 plus 2 electrons. So there's going to be 2 electrons for every 1 mole of 10. So that's going to be a 2. So I would write out that half reaction, kind of like you did up here, but write out the half reaction. Otherwise, you make mistakes like that. Okay. No, you have to go all the way to moles of electrons. So write out all your units. Grams of 10, moles of 10, right? And then moles of 10, moles of electrons. So I would write the half reaction so you know what the mole bridge is. 10 goes to 10 plus 2 electrons.
I keep writing.
So any problems with EX4? We're good? Kendall, did you get it? It's close. He got 2.49. That's close to 2.5 to 10 to the 4th. So here's some good practice. Find the overall cell reaction and the standard EMF for each. So remember the game plan for this. A couple people got 1.51 volts for a E0 cell here.
I got 23. I got 23 too.
Oh, you guys are getting 0.3s. We might want to write this one out. All right. Chromium goes to chromium plus 3. Yeah, it should be like 0.3 or something, right? 0.33. You see where you guys messed up? Connor, you see where you messed up?
Ours says 44. Yeah, ours says 44.
Yours is, why is my table different than yours?
Well, which one's right?
Let's use yours. So bottom 1 times 3, top 1 times 2. So my electrons will cancel out. And last one. Anybody get an E0 cell for the tin one? What'd you get? 0.01? 0.01 in the back? 0.27? Yeah, I get 0.01 volts. All right. All right, so have a good evening. Have a good day.